Let's make sure. Okay. All right, so this is Physics 1B for 1376 for September 20th, and we're going to be talking about a few different fluid dynamics problems today, and then we're going to start talking about thermodynamics. We're going to discuss temperature, thermal expansion, and maybe calorimetry. So let's get started. All right, so the first thing that we're going to look at are these two fluid dynamics problems, and this first one is called water pressure in the home. Let me make it a little bit bigger. So what we have is this picture down here where we have water coming in at the bottom, and it says that water enters the house through a pipe with an inside diameter of 2.0 cm. So that's down here. I can't really, oh, it says it right there, so that's nice. So we have 2 centimeters, and that's a diameter for the pipe. At an absolute pressure of 4 times 10 to the fifth, or about 4 atmospheres, okay? So we know the pressure at this point, we're going to call this point 1. We're going to call pressure 1 and say that it's equal to 4 times 10 to the fifth pascals. A 1 centimeter pipe leads to the second floor. So this pipe right here, I think it's still the blue pipe, the skinny blue pipe right here. There's a 1 centimeter pipe here at point 2. Can't really draw that in a picture, but it is written right there. Again, that's a diameter. I guess we could call this one down here D1. We could call this one D2 if we want to. It leads to a second floor that's 5 meters above. So we have a 5 meter height difference here. What I'm going to do is I'm going to say that Y1 down here, the floor, we're going to call that 0 meters. And Y2 right here, let's see if I can write it up here. We'll write Y2 is going to be equal to 5 meters. So we're 5 meters above. When the flow speed in the inlet pipe is 1.5 meters per second, so they're saying given that the velocity of the flow down here is 1.5 meters per second, we want to calculate the speed, pressure, and volume flow rate in the bathroom. So I guess, yeah. So there's a bathroom here, which I guess you can see because there's a sink, and there's a toilet, and there's a shower, each which have hot water coming in, and they have cold water coming in. We're just looking at the cold water. And we're supposed to figure out at the top inside of the bathroom right here, how fast is the water flowing? And we also need to figure out the pressure at that point. And they also want us to find the volume flow rate. So the last thing we'll find is the volume flow rate. Okay. So which one of these would be the best thing to start with finding? What do you all think? How should we get started? Which one of these two quantities here, velocity or pressure, do you want to find first? Okay, I agree with velocity. Why do you think velocity is better to start with, Joe? We could start with pressure, but it would lead to, we'd actually have to find the velocity to get the pressure. That's mainly the reason. Use the continuity equation? Yeah, let's do it. All right, so there's no part A or B here. So first thing we're going to do is we're going to find the velocity at point 2, right here. And that means we're going to be using the continuity equation. Can rearrange it. Nope, that's upside down. Okay, like that. For the areas, we have diameters, so we're going to use the area of a circle, which is pi times radius squared. So we have diameter. At the bottom, it's 2 cm. So here we're going to write at the top 1 cm because that's the radius squared. And for A2, the diameter is 1 cm, so we're going to write the radius is 0.5 cm. So that's the ratio of the areas. It's going to give us a factor of 4. We multiply that times the velocity at point 1, which was 1.5. And if we work this out, you've got basically 1 over a half, which is 2. You have to square both of these, my bad. 2 squared is 4. 4 times 1.5 is like 4 times 15, which is 60 divided by 10, which is 6. I think that's 6. So that's one part of it, the velocity. Anyone have any questions about that? So we found the velocity first. because when we use the next equation we need to use to find the pressure, which will be the equation we derived in class last time, continuity equation. Sorry, the Bernoulli's equation, excuse me. Shouldn't be talking while I'm writing all the time. So Bernoulli's equation says that if we take these quantities, sorry, my email is making noises, so we're going to close this. All right. So we use Bernoulli's equation. Bernoulli's equation relates pressure, velocity, and height, which we have in this problem. You know, we have all those three quantities here. We've already found this one, and we want to find this one. So Bernoulli's equation is good to use for that. Oops. I2. Okay. And now it's just a matter of plugging all the data that we have in here and solving for the one unknown that we have, which is P2. So let's rearrange. Just as a reminder, every time you do these kind of problems, I really want you to, as much as possible, plug all your numbers in at the very end after you have done as much algebra as you can. So I'm going to rearrange everything here and say that this quantity should give me the pressure 2. And now we just have to be careful about as we plug things in to make sure we keep track of units and things. I don't know if I'll be able to fit all this in here, but we'll try. All right, so pressure 1 was 4 times 10 to the 5th pascals. The density that we're dealing with here is water, so we're going to have 1,000 every time we see a row. You know, I guess what we could do, just because there's no way I can write out and fit all that in, is we could do one more step of algebra here and factor out the row from every one of these terms. Of course, if I factor it out, I don't have to rewrite it. 1/2 V2 squared minus G times Y2 equals P2. There we go. Okay, now plugging everything in, we'll have still gonna be pretty hard to fit all this stuff in here. Okay, 1/2 V1 squared. V1 was 1.5. 1.5. G times Y1. Y1 was 0, so actually don't even need to write this one in here actually, because we can just go in here and say that Y1 is 0. Probably should have done that a few steps back. Minus 1/2 V2 squared, so V2 is 6 from here. And then minus 9.8. I'm going to be hitting this thing here, so I'll just scroll down. So 9.8 multiplied by Y2, which is 5 meters. And that's equal to P2. Maybe this is too small for some of you to see, so maybe what I'll do is, let's take this entire equation here, let's move it down here where we have some room, and let's just make it bigger, because then it should be a little easier to see what's going on there and what you need to calculate. So I don't have my phone with me. I will be right back. Can you all calculate that for me and tell me what you get? Okay, you all seem to agree. That seems reasonable. It's less than the pressure at the bottom, which is also reasonable. Does anyone disagree that you get pressure at point 2 is equal to 3. I'll just call it 3.3 times 10 to the 5th? Sounds right to me. Seems like a reasonable number. Sorry, I have to put a close bracket on there. Okay, anyone have any questions? That's a pretty straightforward problem, but it doesn't hurt to start with something that's very straightforward. I mean, I say it's straightforward. It may not be for you. I don't know. But in terms of, as far as a Bernoulli's kind of problem goes, you're basically just given some data. You need to make sure you indicate, what data all goes at one point, and then what data all affects another point, right? And then you just kind of fit everything in here, remembering that one of the steps you're probably going to need to use is this one to relate the velocities. All right, so let's go on to the next one. I think this one is relatively similar to the problem that you all had been asking about. There were 2 questions about it this morning from the homework. So this is called what's this? My audio mixer set Discord's volume to 0, so I didn't hear what you had to say about that one mastering physics problem about Mercury when you upload the stream to YouTube. I'm never going to upload the stream. No, I'm kidding. I always upload things right after class. And if I don't get it right after class, I'll get it by the end of the night. Mondays are kind of unique in the sense that I have like a 14-hour day. I start at, the stream starts at 9:45 a.m. and I usually get home at 11 p.m. So it's more like 13.25 hours or something like that. So like right after this class ends, I need to like shower, eat lunch, and then I have another class, and then I have to go to school. So I will try to upload it, Christian, but it might not be uploaded immediately. You know what I'm saying? And we can talk more about that problem after class too, if you want. Okay. Have any of you have all the? I've uploaded all the lectures, right? Like no one has had any problem finding a lecture, right? Let me know if you have. Let me know if there's something missing. Anytime that your question's fine, Christian, but I would rather see you ask me like, if I don't upload it, let me know. You know what I'm saying? But assume that I'm probably going to upload it. If you don't see it tomorrow morning, like that's a problem. If you don't see it until like 9 p.m. tonight, well, that just might happen. So, yeah, I'll try. I will try as hard as I can to upload it today, though. Like, there's really not much of a reason I shouldn't have to do that. But you never know. Never know what's going to happen during the daytime. I may get distracted answering questions from students. Okay, so another problem. The Venturi meter. It's used to measure flow speed in a pipe. We want to derive an expression for the flow speed V1. So the flow speed here, V1. In terms of the cross-sectional areas A1 and A2, and the difference in height, H, which they're labeling up here as H, the height here between this piece and this piece, of the liquid levels in the 2 vertical tubes. We have a tube like this that I could show you it when we're on campus, this actually happens. I guess one thing to think about is, what would the level in this this tube on the right be? What would the level there be if the water wasn't flowing? Does that question make sense? What would the level of the water in this pipe be, you think, if the tube wasn't flowing? Would it be the same level? Would it be higher? Would it be the same level as the other one? What do you all think? They would be the same. And how do you know that? Same level. So everyone seems to agree. How do you know it would be the same level? How do you know that they would be at the same level? No changes in pressure means it equalizes out evenly throughout the pipe. Yeah, I think that's right. Water always tends to find this balance, right? No matter what the shape of the object you're looking at is. Again, this is something I can show you when we go to campus, but no matter how this object is shaped, if the water's not flowing, then there has to be a balance. I think of it as like the same way that if you take 2 objects and you put them on a scale, I'm talking about like a scale that can kind of move up and down like this. There's 2 sides to it, right? If I took 2 equal weight objects and put them on the scale, then it balances, right? And the water in the pipe is very similar, that if the fluid's not flowing at the bottom, then these 2 levels have to balance, because otherwise, if the height up here is higher, then the water's going to want to push down to make this height go higher and balance it out. So, but that's not what's happening here. What's happening here is that there is a fluid flowing through here, and as we know, fluid flow has the effect of reducing pressure, right? So we have to, So we're supposed to find the flow speed V1 of the cross-sectional areas, A1 and A2, and the difference in height in this particular case, right? So let's do that. So we already have an area here and an area here and two different velocities, right? So one of the first things we can do, just like in the last problem, right, is to use the continuity equation. And the one that we're going to want to find in this case is V1, right? So we're going to eliminate V2 by saying that V1 is equal to A2 over A1 times V2. And then the other equation that we want to use is Bernoulli's equation. Doing. Okay, so what are we going to use for y2 and y1? We already kind of have a relationship with v1 and v2. P1 and P2 are something that we don't really know necessarily, but are obviously going to be part of what's going on here. What do we know about y1 and y2? What is that equal to? y1 and y2. Do we use the height of this fluid up here? You know that putting them together makes h. Putting them together like y1 plus 2, y2 equals h. Or the difference between the two of them equals h, is that what you mean? y1 minus y2 equals h, okay. So you're saying that y1 is this, and y2 is this, right? Is that what you're saying? That we should use y1 here and y2 here? Yeah, I don't really agree with either of those statements. And I could say why, but I would look for someone else to think about this. I don't think that's what y1 and y2 are. I don't think that's what it is. I don't think that's what is meant by Bernoulli's equation. I think it says something else. What does Bernoulli's equation say? When it talks about this y1 and this y2, what is it talking about? We could go back to the picture that I drew. Can't remember what I did with this class. I can't remember if I drew a picture, if I used the picture from the book. I think we used the picture from the book. Yeah, we did. So I'm just going to pull this over here. Expand it. So this was our picture we used for Bernoulli's equation, right? And we had a fluid that started down here and it flowed up to a certain height. And notice where's the y1 measured to? That's right, Kelvin. y1 and y2 in Bernoulli's state the actual change in heights of where your flow water starts and ends. That's right. Here and here. The same height at point 1 and point 2. The same height, exactly. They have the same height. It's very tricky. It is very tricky. It seems like you should use this, right? But the reality is that the fluid is flowing through here. And what's happening in these pipes above the fluid, I believe this is correct, is a result of the flow of the fluid, right? So I started this off by asking the question, what would the pipes look like if there was no fluid flowing? And you all answered correctly that they would both be at the same level. It'd be somewhere in between, right? It'd be like, they'd both be at a level like somewhere right here, right? As a result of the fluid flowing, the pipes change these heights, right? But in terms of Bernoulli's equation and what it describes, the height that it describes is the height of the fluid, and it's really the height of the center of the fluid. So if you have a pipe, you find the height up to the center. Okay? So in this particular problem, the way we would define it is by saying, let's say we say the bottom of this thing is 0, then this is y1, and the same thing over here is y2. Because it's right to basically where that point is, right in the center of the pipe. Okay? That means that y1 equals y2, and that also means that for our equation over here, which barely fits on the screen, we can cancel those terms out because they're equal to each other. Not because they're 0, although we could choose them to be 0. We can cancel them out because they're equal to each other. If we do that, then we're kind of almost done. We just need to replace some things. So now what we would write is that P1 minus P2 should be equal to... Is this the best way to do this? Sure. P1 is going to be higher than P2, right? That's what Bernoulli's equation tells us, is that fast-moving fluids exert less pressure. P1 is higher than P2. Let's write it like that. Let's move everything else to the right-hand side. So we'll have 1/2 rho V2 squared minus V1 squared. So I just subtracted this term over to the right-hand side. We can then plug in so V2 squared is going to be, I lied. I was thinking too far ahead and I got it wrong. We need to eliminate V2 because our goal in this problem is to find the flow speed V1, right? So our goal is to find what is V1 equal to. So that means we actually have to eliminate V2 here. So A1 over A2 times V1 is going to be V2. Plug that in for V2 right here. All of that squared. Let me make this parenthesis a little bigger out here. Minus V1 squared. Then we do some rearrangements. P1 minus P2 multiplied by 2 over rho from here, multiplied by this factor, equals factor out of V1 squared. So we'll have A1 squared over A2 squared minus 1. Divide this to the left-hand side. Divide to this piece. So A1 over A2, both squared, minus 1. This is all going to be equal to V1 squared, which we can then square root away. And that is almost the answer. We're not quite there. Now, if we look back to the problem and reread what they're asking us to find, okay? You could say, are we done? We have V1, right? There's no numbers, so it's kind of hard to know. But in the problem, it says, derive an expression for the flow speed V1 in terms of the cross-sectional areas A1 and A2, and the difference in height H. So are we done? Or do we need to do anything else? Are we done, or do we need to do anything else? This is directly related to the question you asked at the beginning of class, James, or the email you sent me. And the other person that came in late, Del, said that you were saying you were confused about that problem. This is exactly the answer to that problem. This is the same problem, basically. It's just a little bit different. Do we rewrite pressure to include height? We do. Yeah, we need to get H on our final answer. That's right. We need to remove pressure. Okay, you're all exactly right. It's exactly right. Very good. How do we do it? So let's think about the pressure. P1 minus P2, and someone specifically said what we need to do. Well, you're all general. If you take all your answers together, you're saying it. We need to get H in the answer, right? So H has to have something to do with this. H is, again, the height difference between the two pipes. And it has to have something to do with the pressure difference, right? So what could the pressure difference be equal to in this case? What do you think? Someone actually Christian almost said it earlier. Not exactly right, but close. Yeah, that's the answer. Exactly. So if you go back to our study of variation of pressure with depth, right? You know that a column of water exerts a certain amount of pressure, right? So we have two different columns of water here, right? You've got a column that has a height. What's the best color to use here? Maybe purple, I guess. So you've got this column of water over here that's above this 0.1, and you've got a column over here that's above 0.2. Now, the Venturi meter, the idea of it is basically that these height differences can tell you something about the pressure differences, which of course is related to the speeds, right? So if you have these two different heights, and I know what the pressure is down here, the pressure from the column of water has to be the same as the pressure of the fluid, effectively. I mean, that's the reason why the column of water is dipping down, is because the pressure beneath it is lower, which means the column of water, well, it can't exert as much pressure. So the difference here, which comes from variation of pressure with depth, right, is going to be that the pressure difference is just rho GH, which we can put into our problem right here at the top. So if we do that, we get square root of 2 rho GH divided by A1 over A2 squared minus 1 square root equals V1, and there we go. Now, I hope that helps. This is basically what I think this is basically what you have to do on that problem that you all asked earlier. Problem 8D or whatever it was. So during the break or after class, probably better to do it after class because I do need an actual break when we take breaks. We can come back and we can see if we can help you to understand, what was going on in that problem. Okay, does anyone have any questions? If not, 10:20, we should probably take a break. We don't start till 9:45, right? We can keep going. All right, let's start talking about temperature. So we're going to talk about temperature, the Zeroth Law of thermodynamics, thermal equilibrium, Celsius and Fahrenheit scales, and the Kelvin scale, and how you can use it to relate temperatures and pressures. So let's get all this stuff that we need for this. Let's just talk about these first, and we'll come back and talk about the other one. Click, cut. Isn't P2 minus P1 delta P? Correct. Yeah, Albert. Yep. The difference in pressure? Sure. And that's equal to rho GH. Does that make sense? Ooh. I see what you're saying. You're saying that I had it backwards. Wait, did I? Wait. Did I have it backwards? Hold up. Wait a minute. P1 is bigger than P2, right? This is one of the things I asked during the problem. I said, is this what we want? I said, yeah, P1's bigger than P2. That's true, right? Yeah, it is, because this is the faster moving fluid. So if P1 is greater than P2, then this makes sense, right? If I wrote P2 minus P1, there'd have to be a negative sign on the right-hand side because, again, let me just make really clear what I'm saying here. P1 is greater than P2. Sorry, it's right, Albert. Maybe you're thinking with delta that it's usually the higher value that we, delta P, you're thinking it's like, I don't know, final minus initial or something like that. Is that what you're thinking of? That's confusing you about the delta P? He wrote delta P. That wasn't me, by the way, Albert. Troy said delta P. I never said that. You understand? So don't worry about that. If that's confusing you, if the delta part's confusing you, don't worry about that. I never use those words. It's this right here. Or I may have repeated what he said, but I never wrote delta P. It's just P1 minus P2. Okay, yeah. I knew what he meant. When he said delta P, I knew he meant the difference in pressure. When you say delta, that's all you really mean usually, is just the difference in pressure. And usually you mean that in a positive sense, right? Or, well, in this case, it would be a positive sense. Okay, so let's talk about, temperature. All right, so what does temperature mean? If I was to ask you all that, you probably, what do you say? What does temperature mean when you say temperature? Without reading what's on the screen, just what I mean, when I say If it's 70 degrees Celsius outside, what does that mean? Hot and cold. How hot or cold something is. If you touch something that's 120 degrees, if you knew it was 120 degrees before you touch it, you knew it'd be really hot, right? If you go out to the ocean water around here is it's pretty cold, right? It's probably like in the 50, 60 degrees, 70 degrees, something like that. So you know that before you get into the ocean, it's going to be cold. Measure of heat. I'm not so sure about that, Christian. That's one of the things. I'm glad you said that because heat and temperature are different things, and we have to get really specific about what we mean about that. Okay. So heat is a flow of energy from a hot object to a cold object. That's what heat is. Okay. Now I know that in common parlance, like the way people just generally talk, the words temperature, heat, hot, and cold all kind of mean the same thing, I think, right? So be careful about that word heat. Heat means something specific, and we'll talk about that, I guess today. I guess we'll be talking today about exactly what heat is, but the first thing we got to get is temperature. So temperature is a measure of how hot or cold something is, and generally we measure it on one of three scales, right? Here in America, we use the Fahrenheit scale. So if I say 60 degrees Fahrenheit, I think most people here know what that means, right? Whereas if I was to say 30 degrees Celsius, can you all tell me, is 30 degrees Celsius, like if it was 30 degrees Celsius outside, would it be hot or would it be cold? Or do you even know? I don't actually know. It sounds like it's hot, right? Yeah. What about 40 degrees Celsius? That I think you'd all agree that's definitely hot. I think 30 degrees Celsius is in the 21 degrees Celsius is room temperature. Is that right? Okay, yeah. So 30 would have to be pretty warm. Yeah. Although I do think that in certain parts of the world it does get into the close to 40 degrees Celsius range if you go into desert areas and stuff like that. Maybe I'm wrong. We have to actually do a calculation, which we'll do here in a second, and see what those numbers actually are. All right. So we want to be able to. Vietnam gets to 40. Is that what Vienna is? Vietnam? It gets to 40? Yeah, I believe it. Is it really humid there too? Since it's like kind of, obviously I've never been before, but I get the impression that it's very humid. Is that right? So that must be completely unbearable. What is it like if you stand outside? Does everyone stay inside during that time, or do they get in the water? What do they do when it's 40 degrees and really humid outside? What do you try to do to stay alive so you don't die to the heat? We've had a lot of really, really bad heat waves recently, right? In the Northwest over the summer, a lot of people died. Maybe they're still dying. I don't know, due to a massive heat wave. And they covered themselves mostly. Thinking that makes sense. Did you all read about this? Did you hear about it at all? Did you hear about these deaths that occurred due to a heat wave in the Pacific Northwest? I think it was in Portland, and I think one of the things that happened there was that the cables that run their like trolley lines, streetcars, I think they're called streetcars. The cables actually melted due to the heat. And none of you heard about any of this, right? A lot of people died. It was really deadly. I was listening to a story the other day where a group of people that are involved in environmental concerns, they're trying to start getting heat waves named. You know how I don't know how, maybe you all are too old to remember this, too young to remember this, but do you all remember Hurricane Katrina? Do you all remember Hurricane Katrina? Okay, you do. It was devastating, right? I mean, it had a massive impact on many cities, especially New Orleans. Some of the things that I remember, that people were staying in the Superdome, and there were all sorts of issues with finding homes for people, getting people out alive. It was deadly. This happened, I want to say, in 2005. So if you don't remember it was a really long time ago, but a lot of people did. So these heat waves keep occurring and people keep dying, but nobody remembers them. But the moment I say Katrina, you know exactly what I mean, right? So what these people are trying to do, and I think this is really interesting, is they're trying to start naming heat waves. They want to get a name on it so that people can actually have a memory of what happened, so that it can enter the public consciousness, so people will start caring more about dealing with these issues. Because, it's only going to get worse unless we start to reverse like the kind of climate trends. It is really smart, right? It's not something I would have thought of. There's very clever people that were like, you know what, if we just start naming these things, maybe people will start paying attention. Because like I said, this literally happened a couple months ago. It's on the same coast that we live on, so it's not like it happened in New York. It's not really far away. I suspect some of the people in here, you probably know people that live in Oregon, or if you don't, you have a friend of a friend that's from Oregon or something like that. Point being that it's a problem if big major events like this happen and nobody knows about it. Literally, the cables of their streetcar just melted. Just think about that. You know, what if pieces of Los Angeles started to melt? You know what I mean? What if the rails on the track started to melt, or what if something like that? So anyway, temperature, that's what we're discussing, and that's what we're going to be discussing for most of the rest of the class. The rest of this class is about thermodynamics, and then toward the end we'll be talking about waves, but the bulk of this class is about this thing, about temperature, how it affects things, how it can cause things to expand and contract. And so we have to come up with a good definition of what temperature is so that we can all agree on it. And this is how we do that. So suppose I have a couple of systems. The systems could be anything, okay? Could be an object, okay? So if we take an insulator or a conductor and put them between these things, maybe I should define what these things are. Maybe you already know what they are, but let's define what an insulator and a conductor are. Can you all tell me, when I say conductor or insulator, what do I mean? They can mean something for electricity, and they can mean something for heat flow. What do they mean? What is an insulator for heat flow? You can either give me an example of one, or you can tell me what you think it is. A conductor allows current to pass through. Again, we're not talking about electrical current now. Insulator means like absorb, maybe? Okay. It does have the effect that it can absorb a lot of heat without actually changing its temperature. So the word current, Correa, is your first name Eric? Sorry, I don't remember. It's Emilio. Okay, so Emilio, when you say current, were you talking about electrical current, or did you mean something else? Can you change that to mean something related to heat? Here it is okay to talk about heat. Heat, which is a flow of energy. If you can't think of a definition, can anyone type in the chat what an example of an insulator is? Something that insulates heat really well? What does that mean? Maybe you all just don't know. I mean, I'm not getting a lot of responses. Maybe this is terminology you're not familiar with, which is totally okay. But certainly some of you can think of things that are good at insulating for heat. Bricks, okay. Wood, all right. Wood burns, but it could be good insulator, maybe. What's in the walls of your home? Okay, house insulation, Troy. That's fine. Clothing, fiberglass, okay. What's in the walls of your house? Does anyone know? What are the walls of your house made of? They're obviously made of probably wood or stone or something like that, right? But if you were to like kind of look, drywall, okay. Drywall is on the outside of the wall, right? That's a substance that you layer on top of the wall. It gives it that texture. Foam. Some forbidden pink cotton candy that tastes horrible. Okay. So some places there's foam. A lot of places it's just air though, right? But you're naming some of the type of things that can be good insulators, okay? Examples would be things like foam, like styrofoam is a really good insulator. Styrofoam. Air is an extremely good insulator. In the walls of your house, if you were to like, not suggesting you do this, but if you were to bust open one of the walls of your house, you'd find that your walls are mostly air, because air is a very good insulator, okay? Other examples of things that are insulators would be like a cooler, right? Something that you use to put cold drinks in, and then you put ice into it. The interesting thing about an insulator is it basically slows down the flow of heat. So an insulator basically slows the flow of heat. And to put it another way, it keeps things hot or keeps things cold. It basically keeps them around the same temperature you put them in there at. So, I can use a cooler to keep beverages cold, right? If you want to put a bunch of beer or sodas into a cooler, throw some ice in there, close the top so that, air can't get in from the top, then it'll keep things cool, just like your fridge does, right? But you can also use a cooler to keep things hot. Your fridge, you can't put hot things in your fridge or they'll get cold, right? Your fridge actively cools things down, all right? So your refrigerator in and of itself is not an insulator, but it does have insulating material, right? The actual doors and stuff. It's designed to make things cold. So we're not talking about a refrigerator here. We're talking about something to keep things either hot or cold, right? So if I have a cooler and I don't put ice into it and I fill it up, like there's a guy that walks around my neighborhood and he sells tamales, and he basically keeps all the tamales in a cooler, and it keeps them hot. So when you walk up and buy a tamale, then it's going to be warm, right? So that's because the cooler can keep things hot or cold. Same thing can be said of like thermoses. Like I have a thermos that I keep my coffee in when we used to go to school. A thermos has a lot of properties that make it really good at keeping things hot or cold. But inside of a thermos, what you have... Do I want to draw this? I don't know if I can draw this. Probably better to just go find a picture. So a thermos, what you have is you have some inner portion, and then it has an outer layer that you obviously can't normally see. And usually what happens is that this part is filled with like air or foam. So this part in here is basically just filled with maybe something similar to that kind of foam that you talked about, that you found in your walls. That's also a type of insulation that you were describing. So we call this a thermos. I think that's the name of these things. And it has other things that help it to stay cold. So normally sometimes thermoses might have a reflective coating on the outside. Having like a reflective coating with something like stainless steel or something like that makes it so that energy coming from the outside through radiation, from the, like sun's rays, for example, can bounce off of it. But the biggest thing is it's filled with this, it's filled with either foam or air or something like that. And a thermos has the effect of basically keeping things hot or cold. And this is an example of an insulator. Okay, it slows down the flow of heat. It keeps things hot or cold. It does not permanently guarantee that things will stay cold forever. For example, if you have a cooler and you put a bunch of sodas inside of it and you have ice inside of it, you close it up. What happens after about a day to all the ice inside of that cooler? If you open it up the next day, is there going to be ice in there? It's all going to melt, right? So that tells you that an insulator is not perfect, and that's important to understand. An insulator slows down the flow of heat, but it cannot prevent the flow of heat. I don't think that we know of any type of substance that can actually stop heat flow. Does that make sense? There's no substance that can completely stop heat flow. And that makes heat a lot different from electricity. I know that maybe a lot of you haven't studied electricity, but electricity, you actually can create a region over which electricity cannot flow very, very easily. But with heat, you just can't do it. Heat will always get through. There's nothing you can do about it. Okay, a conductor is the opposite of this. A conductor basically allows heat to flow really, really well. And some examples of a conductor. What do you all think? What are some objects that you think allow heat to flow very, very well? A pan, okay, like a metal pan that you would cook with. So the pan that's made of like metal or something, right? So metals, yeah, copper, yeah, any metal you choose is going to be a good conductor of heat. I think all metals are good conductors of heat. Metals also happen to be good conductors of electricity, and the reason for that is because electrons are the thing that are conducted with electricity, and it turns out that when you heat something up, it's actually electrons that allow the heat to flow really well. Water? Is water a good conductor of heat? I don't know about that. Water can store a lot of heat. I don't know that I would call it a good conductor of heat. And here's a good experiment that you can do to prove why I think this is the case. If you take a pan and you put it on a stove, you turn the stove on, the pan itself will heat up really quickly, right? The pan itself will heat up really quickly. I think glass can conduct heat pretty well, yeah. I think if you have enough of it, it can act as an insulator, but I'm not so sure about glass. We'll put it down here, though. Certain types of glass, I think, conduct heat pretty well, like Pyrex. I think maybe we put Pyrex here. I think that's acceptable. I think Pyrex can conduct heat pretty well. That's what you often use that's the type of glass that you use often in like your chemistry classes, I believe. Like a lot of the things that are going to be heated up. Anyway, so conductor, something that allows heat to flow very well. What I was trying to say about water is you take a pan, you put it on the stove, right? You light the stove so that there's flames down here, right? Here's your pan. You also, inside of this pan, you put liquid water. Okay, so we've got water in here. We're trying to heat it up. Now, your pan's made of metal, right? If you were to turn the stove on, leave it on for, let's say, like, I don't know, 10 seconds or something like that. Not a very long time. Very short amount of time. After 10 seconds, if you were to touch this portion of the pan without touching the fire, would you think that would be a safe thing to do? after the pan had been on for like 10 seconds? You all would agree no, right? And why is that? Well, because the pan is going to heat up really quickly. What about this? What if you dropped a spoon inside of here and you want to reach in and grab it? You think that's going to be safe after about 10 seconds or so? Like you literally just turned it on. It hasn't been on there very long. You think you can put your hands in the water safely? Definitely. You can, for sure. And why is that? It's because the water actually takes quite a bit of time to heat up. It takes quite a bit of time to heat up. So that's why I don't know if we can put water as a conductor here, but maybe it's classified as a conductor. I don't really know. The good thing is that as we're discussing conductivity in this class of heat, we're eventually going to have a table that tells us exactly how much conductivity something has. I don't think it's on this page, but it will be in a later class that we talk about. We can quantify just how good some of these things are at slowing down heat flow and just how good other things can be at allowing heat flow. Okay. All right. So conductor, insulator, we've defined what they are. It seems important because now we're going to use this this picture right here to define how temperature is working. Okay. Insulator slows heat flow. Conductor allows heat to flow very well. So we have this system right here, right? And the system is made of, well, this is made of system A, system B, and system C, okay? And system C has a conductor that connects to system B and system A, right? But there's an insulator, indicated by this green thing here, between system A and system B, right? So what that means is that system A and system B are going to come into thermal equilibrium with system C after a certain amount of time. Yeah, that's not clear enough. We'll just write this sentence twice and just change it. So after some amount of time, object A is going to be in thermal equilibrium with object C, and also object B is going to be in thermal equilibrium with object C. And the reason for that is these conductors right here. So what do I mean by thermal equilibrium? Can anyone tell me what they think that means? You've obviously learned about equilibrium in your Physics 1A class. Probably learned about equilibrium if you took a chemistry class, like an equilibrium that can occur between a chemical reaction. And maybe you've heard of it in other places as well. What do you all think thermal equilibrium means? The flow of heat between the bodies is equivalent, basically the same level of intensity between all connecting parts, okay? Heat in is equal to heat out. Yeah, very close. Very, very close. You're all hitting on the kind of key parts of what this means. I would say it means that there's no heat flow, or very little heat flow. No heat flows from one body to the other. Is that the same thing as heat in and heat out? I don't know about that, but maybe you're thinking, maybe what you're saying means the same thing, and I'm just, the way I think about it is a little bit different. So thermal equilibrium means no heat flows from one body to the other. So would you all agree that if I place a conductor right here between touching system A and system B, and I tell you that a conductor means that it allows heat to flow very well, whereas an insulator means it doesn't allow heat to flow very well, would you agree that in this particular case that system C and system A would eventually come into equilibrium with each other? That's right, Christian. When you say heat flows down, you mean from hot to cold, right? Yeah. Yeah, I don't know. I think it's probably worth saying, and I think it's something we're going to prove later on, but I'm just going to tell you now, because it's a good general rule to know, that heat is the transfer. I'm going to put X for, that means transfer of energy from, it's technically thermal energy, hot body to cold body. It does not go the other way. Again, I have to prove this to you. We'll prove this later on in class. I think we're going to prove that. So heat is the transfer of energy from a hot body to a cold body. So thermal equilibrium, no heat flows from one body to the other. And yeah, exactly as Christian's saying, if the heat only goes in one direction, it only goes from hot to cold. Yeah. All right. So does that seem reasonable to everyone? That after some time passes, that A will be in thermal equilibrium with C and B will be in thermal equilibrium with C, if we just look at picture A. That makes sense? Heat will be able to flow from this one to this one. Let me give you kind of an example just of how this would occur. Suppose that system C started at 60 degrees Celsius and system A started at, let's say, 20 degrees Celsius, and let's say system B started at 30 degrees Celsius. Okay. System C is hotter than system A and B, right? So what's going to happen to system A and system B? Is system A, is its temperature going to increase or decrease after some time? If system C is 60 to start with, system A is 20 to start with, and system B is 30 to start with. So system A, its temperature is going to go up, right? So system A is going to get hotter. Its temperature is going to increase. What's going to happen to the system B? Is the temperature going to increase or decrease? It's at 30. It's in thermal contact with 60. The insulator here, keep in mind, this stops the heat from flowing between A and B. It doesn't completely stop it, but it slows it down considerably. So what's going to happen to system B? Is its temperature going to go up or is it going to go down? It's 30 degrees. System C is 60 degrees. It's also going to go up. That's exactly right. So the temperature of object B will also increase, right? What's going to happen to system C? It's touching, this is a hot object touching two cold objects, right? What's going to happen to its temperature after some time elapses? It'll go down, right? It has to, right? So the temperature of object C is actually going to decrease, right? It'll go down. Now, I don't know what kind of temperature these three systems are going to reach, but I do know that after some amount of time, right? So I'm going to put over here that this one started at 20, this one started at 30, and this one started at 60, right? Okay. So temperature A has to go up, right? We know this number has to go up, we know this number has to go up, and we know this number has to go down. And by how much? We'll learn how to do this, but it depends on how much material you have, and it depends on what type of the material you have right here, okay? So if these things are all aluminum, for example, then they're probably going to reach the same average temperature, but it's going to depend on how much mass you have, and we'll learn that later. For now, let's just roughly say that approximately, let's say that everything reaches a final temperature of, I don't know, 40 degrees Celsius, okay? So let's say after some time has elapsed, this is 40 degrees Celsius, this is 40 degrees Celsius, and this is also 40 degrees Celsius. Does that seem reasonable? I don't know. Maybe. We don't know how much material there is, so any number I pick, you could come up with numbers that would make sense. So when I say that A is in thermal equilibrium with C, what I really mean is they have the same temperature, right? But we're trying to define temperature, and that's why I didn't put this stuff up here first. For system B to also be in thermal equilibrium with system C, the only way that's going to occur, right, that is to say with no heat flow, is if they reach the same temperature, because now the heat can't flow anywhere. Right? And that's basically what we mean by this when we're talking about thermal equilibrium. When I say two objects are in thermal equilibrium, it pretty much means they have the same temperature, right? So that is the beginning of thermodynamics with the Zeroth Law as written down here. Let me expand this so you can actually read what's written here. The Zeroth Law of thermodynamics says that if I have a system C, here's system C, right, that's in thermal equilibrium with both A and B, then A and B are also in thermal equilibrium with each other. So if these two are both in thermal equilibrium with the same object, that means that system A has the same temperature as system C, system B has the same temperature as system C, and therefore A has the same temperature as B. Does that make sense? This is like saying, if in math, right? In math, if I gave you some relationships and I said, I know that A is equal to B, and I know that, no, whoops, that's not right. I know that A is equal to C, and I know B is equal to C. Therefore, what can you say? A is equal to B, right? That's all that we're saying. Does that make sense? If A is equal to 1 and B is equal to 1, then, well, 1 equals 1. Obvious statement, right? So then we can take that statement and then we can make this statement. Two systems are in thermal equilibrium if and only if they have the same temperature. The only way that systems can truly be in equilibrium with each other is if they have the same temperature. And that's our definition of thermal equilibrium. That's how we're going to know whether things have heat flow or not, is through temperature. Okay, does that definition make sense? We should take a break right now. Anyone have any questions? Okay, we're going to take a break until 58 after. 10:58. So those of you that had asked the question earlier about that problem, can you think about it, like we have some time now, think about it during the break. Go back and maybe retry it if you have time. If you don't, that's fine. And then we'll talk about it at the end of class, okay? The mastering physics question you'd asked about. I hope that having done this problem with you together, I hope that helps you a little bit with that problem. So, all right, take a break. Scroll down just a little bit here.